Welcome to the video lecture series for Texas A&M University course Math 152. Today we will take a look at section 10.3, Integral and Comparison Tests. You can find the accompanying handouts at bit.ly/RaeleneMath152. Let's begin. In the warm-up for number 1, we want to know if the following series converge. Let's recall the nth term test for divergence. The nth term test for divergence does not tell you if a series converges but only if it will diverge. It says that the series from n equals 1 to infinity of an diverges unless the limit as n approaches infinity of an equals 0. Now, this does not say that because the limit as the nth term of a sequence an goes to 0, that the series converges. It's similar to when we said if we had an improper integral for a function f of x, and if the integral from 1 to infinity of f of x dx converges, then it's not necessarily true if we have a function higher than that function, let's say g of x, the integral from 1 to infinity of gx dx may converge or it may diverge. Similarly, if we have a function whose integral diverges and we have a smaller function than that first one, its integral may either converge or diverge. We don't have any conclusion. Similarly then, for the nth term test for divergence, just because the nth term of a sequence goes to 0, it does not conclude, or we cannot conclude, that the series will converge. But we know for certain that if the nth term doesn't go to 0, that the series must diverge. So we can use that in number 1a. The nth term is an equal to n, and here the limit as n approaches infinity of an, which is n, equals infinity. And so because this limit is not 0, we know that by the nth term test for divergence, this series diverges. So I'm going to write that in a bit better detail on the next page. Okay, so the series from n equals 1 to infinity of n diverges by the nth term test for divergence, because limit as n approaches infinity of an, which equals the limit as n approaches infinity of n equals infinity, which does not equal to 0. In part B, we have 2 to the n plus 1 over 3 to the n. And so we have the sum, rather, of n equals 1 to infinity of 2 to the n plus 1 over 3 to the n. This is a geometric sequence term because the variable n is in the exponent, and I'm going to rewrite it a little more clearly in the form of an equal to a times r to the exponent n. So using exponent laws to pull this apart, I see that this is the sum from n equals 1 to infinity of 2 times 2/3 to the exponent n. We know that the series, a geometric series, will converge if r is between -1 and 1. We saw that in 10.2, and therefore we have a convergent. Well, let's state the value of r here. We can see that r is equal to 2/3, and we have a convergent geometric series. So not only do we know that we have a convergent series, but in this particular case, we could state what the sum of the convergent series is. The convergent geometric series has a formula given by a over 1 minus r, as long as r is between -1 and 1. And in this case, we get 2 divided by 1 minus 2/3, which is 2 over 1/3, which is 6. In part C, we have the harmonic series. And so for the harmonic series, we have that an is equal to 1 over n. And let me just be clear, that arrow belongs to the series, not to the nth term of the sequence. And so we have, by the nth term test, if we were to take a look at the limit as n approaches infinity of 1 over n, we get 0. So we cannot conclude by the nth term test for divergence if the harmonic series converges or diverges. However, we proved that the harmonic series diverges because the limit of the nth partial sums approached infinity. So we proved that this series diverges, and we did that in 10.2. Okay, let's take a look at one more. Well, we'll go through them as quickly as we can. In the next one, part D, we've seen this one already, where we look at 1 over n squared plus n. It was an exercise from section 10.2, and we can break this apart as 1 over n times n plus 1, which we can pull apart by partial fraction decomposition. I won't show the partial fraction decomposition, but you should practice it here and make sure that you can work out the numerators a and b. And we find that a is 1 and b is negative 1. So this looks like the kind of term for telescoping. So I'm going to let this be s for sum. And so now we have that s is equal to the limit as n approaches infinity of the sum from I equals 1 to n of 1 over I minus 1 over I plus 1. And from here, if we do the telescoping and save the limit for the end, we can come up with an expression. Really, we're just focusing on the expression in the green box and coming up with an expression for s sub n. And so let me do that here. S sub n is going to equal 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus dot 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 plus the second last term plus the last term. The last term is going to be when I is equal to n, so we get 1 over n minus 1 over n plus 1. The previous term, I was equal to n minus 1, and we get 1 over. We have now also when I is equal to n minus 1, that the second term, this is going to be 1 over n minus 1 minus 1 over n. And the terms that cancel are all of the inner terms, and we are left with 1 minus 1 over n plus 1. So from the telescoping, we can see that the sum of the series, if the series converges, is the same as the limit as n approaches infinity of the term for the nth partial sum. And the nth partial sum term is 1 minus 1 over n plus 1. And thinking of this in terms of the right end behavior of a rational function, we get that this limit is equal to 1. So not only do we know that this series converges, we also know to what it converges. Because we can find the sum, we know for sure that the series 1 over n squared plus n converges. And we did telescoping in this particular case. So we've got two special kinds of series, one that we can come up with the nth partial sum term by telescoping, and the geometric series with convergent values for r, that we can actually come up with the sum. Otherwise, we can use the nth term test for divergence to know that if the nth term of the sequence an does not equal 0, then the series cannot converge. We've got two more series here, and I'll leave you to think about the nth term for each one of these and what happens as n approaches infinity. And you can find these completed in the video lecture notes at the end. In number 2, we want to evaluate the improper integrals if they converge. We are not interested in the integrals from 0 to 1 any longer because we are trying to make a connection between the improper integral and a series from n equals 1 to infinity. We have an infinite series, that's why we're not interested in the series from n equals 0 to 1. Well, we simply need to note that these are integrals of the form 1 over x to the p, and we know that the integral from 1 to infinity of x to the p dx will converge to 1 over p minus 1 if p is greater than 1. So in part A we have that p is equal to 9 over 2, and therefore the integral, I'm just going to call it I for integral, will equal 1 over 9 over 2 minus 1, which is equal to 2/7. In part B, p is equal to 1, therefore we have that the improper integral, and not the function, diverges. And in part C, we have that p is equal to 1/2, and again we have diverges. In number 3, we want to determine and justify whether or not the improper integrals converge. In the first one, we have that x squared is going to be less than x squared plus 5 for x greater than or equal to 1, and therefore 1 over x squared will be greater than 1 over x squared plus 5, which implies that for positive x values, x over x squared is greater than x over x squared plus 5. And so we can let f of x equal x over x squared, which is 1 over x. So we know that the integral from 1 to infinity of 1 over x dx diverges, and the function f of x is greater than the function in the integral that we're given, but by the comparison test, this produces no conclusion about the convergence of the given integral. So we actually can't use the comparison test with p equals 1 to make any kind of conclusion about the convergence of this integral. So we have inconclusive for this particular integral. Maybe we'll have better luck in part B. In part B, we can take a combination of the squeeze theorem based on the boundedness of sine x and an appropriate choice of the denominator version for p. So let's rewrite this one. We have the integral from 1 to infinity of sine squared x over the cube root, I think it's the cube root, of x to the 7 plus 1 dx. So here we're going to note that negative 1 is less than or equal to sine x, which is less than or equal to 1, which implies that 0 is less than or equal to sine squared x, which is less than or equal to 1. Therefore, I'm going to label this function here g of x. We are going to get that 0 is less than or equal to g of x, which is less than or equal to 1 over the cube root of x to the 7 plus 1, which is going to be less than or equal to 1 over the cube root of x to the 7, because we know that increasing the denominator decreases the overall value of the fraction. And so we're going to take this last function to be f of x. So now the integral from 1 to infinity of f of x dx has a p-value of 7 over 3, which is greater than 1. So this converges, and by this I mean not the function f of x, but the improper integral involving f of x, converges to 1 over p minus 1, which is 1 over 4/3, which is 3/4. And so that integral converges to 3/4, and since we can put since here, and then we can put since this, and the fact that f of x is greater than or equal to g of x. Therefore, by the comparison test, we know that the integral from 1 to infinity of g of x dx converges. Okay, I'll leave you to try part C, and you can check the final answer on the completed lecture notes. In number 4, we want to consider the infinite convergent series, 1 plus x squared plus x cubed, etc. And in part A, we are going to express the series in sigma notation. So whenever we're using sigma notation, we need to identify the pattern and to see what quantity is changing. In order to do that, we might want to write all of the terms consistent with the pattern. And so the first term is x to the 0, the second term is x to the 1. So what's changing is the exponent on the base of x, and I'm going to let that exponent be I. Now I know that I is an exponent going from 0 to infinity. And so I have the sum from I equals 0 to infinity of x to the I. I could also rewrite that as the sum from I equals 1 to infinity of x to the I minus 1, but there's no need to start the summation at 1. It can start at any integer value. In part B, we want to determine the sum, and so what we need to recognize is that the given sum is a geometric series, or the series is a geometric series. So we could say we have a geometric series, and the common ratio from one term to the next is the constant that, or the constant value that we're multiplying by. And so we see that we have r equals 2x. And so the sum of a geometric series is equal to a over 1 minus r. We see that a is the leading term, which is 1, and r is equal to x. So the sum is actually equal to a rational function, 1 over 1 minus x. And then in part C, if we want to talk about domain restrictions, we can simply look at the domain restrictions of the rational function. So in part C, we have that if we had a function f of x or y, which is the sum, equal to 1 over 1 minus x, we know that for sure x is not allowed to be 1 from the rational function. But furthermore, in order to have a convergent geometric series, for the series to converge, we have an added restriction. We know that the absolute value of r must be less than 1. In other words, r must be be between negative 1 and 1. And therefore the domain is negative 1 less than x less than 1. And so we want to talk about how else x and the domain can be interpreted. Well, we can see that we're talking about the domain as being, well, x is the ratio, the common ratio, and x is an interval on which the infinite polynomial is equal to the rational function. And so we talk about x as the common ratio. And the domain is what we call the interval of convergence. And that's in order for the infinite series to be represented as the rational function. So later on we're going to represent series as functions. And it's worth taking a moment just to look at a sequence of pictures here. If we take a look at the graph 1 over 1 minus x, defined from negative 1 less than x less than 1, we get a graph like this. And if we take a look at the sequence of polynomials, we get y equals 1, and then y equals 1 plus x. And so what we know here is that this is just the tangent line at the point of tangency being x equal to 0, the center. And we see that in fact the curve and the line look alike when we zoom in far enough. In other words, the purple line is the line of tangency, the tangent line, to the blue curve when x is 0. And if we add some more terms, we can see that the two curves have the same amount of curvature, and then we can keep adding more and more terms. And what we're noticing is that the finite polynomial is matching a wider and wider interval of x values on the blue curve. In theory then, if we could add an infinite number of terms, then we could exactly represent the blue rational function as a series, as an infinite polynomial. And we can actually use series notation if we say that y is equal to the sum, we can do summation, from k equals 0 to 5 of x raised to the k, is going to be the exact same as the purple graph. So if I turn off the purple, that's the same thing in red. So I can actually put more terms here. Instead of adding plus x to the 6, I can just change the upper bound. I can change it to 7. I can change it to 8. And if I restrict this so that the x values, let's see if I can restrict this, if I can get off this expression, from -1 less than x less than 1, we see that, in fact, the red polynomial, which is a finite polynomial, is matching the blue curve to a better and better interval from -1 to 1. And so let's see how well the computer program can handle this. Let's go up to 20 terms, and we're seeing very good match almost completely from -1 to 1. But again, this is still approximations to this. Okay, I'll just include that in the lecture notes so you can go back and see the syntax for using summation with graphing calculator. Okay, moving on, let's just review the p integrals. We know that the integral from 0 to 1 of 1 over x to the p dx diverges when p is greater than 1 and greater than or equal to 1, and it converges to 1 over 1 minus p when p is less than 1. Conversely, the integral from 1 to infinity of 1 over x to the p dx diverges when p is less than or equal to 1, but it converges to 1 over p minus 1 when p is greater than 1. And just to ask, does the formula that this is equivalent to look familiar? It looks a little bit like the expression that we saw in the previous example, but we'll leave it at that. We won't bother explaining it. This is foreshadowing for section 10.5. In number 6, we want to evaluate the following limits using L'Hopital's rule. In this case, we know that we have, for the first one that is, as x approaches infinity, the ln of infinity is infinity, divided by infinity is an indeterminate form. And as such, we can use L'Hopital's rule by making the limit of the ratio of the derivatives. So the derivative of ln x is 1 over x, and the derivative of x is 1, and now we have the limit as x approaches infinity of 1 over x is equal to 0. And in this case, we're seeing that the rate of growth of the top function is going to be smaller than the rate of growth of the bottom function, because the limit overall is equal to 0. In part b, the limit as x approaches infinity of e to the x over x squared plus 1 is going to be infinity over infinity again, so we have indeterminate. And so we use L'Hopital's rule, but when we do so, we still have indeterminate. And so we get to use L'Hopital's rule again, in which case we have e to the x over 2, and we're seeing, as we would have predicted, that the exponential function grows at a faster rate than the polynomial function, which is a combination of power functions. And we end up with an infinite value for the limit, which means that the numerator grows, the original function, numerator grows at a faster rate than the denominator. And in part C, we have the limit as x approaches infinity of 5x to the 8 plus lower ordered terms minus, over negative 7x to the 8 plus lower ordered terms. And we have infinity over infinity. And so we can apply L'Hopital's rule not an infinite number of times, but 8 times. And when we do so, we're going to get the limit as x approaches 5 times, then we get 8 times 7 times 8 times 7 times 6 times 5 times 4 times, basically this is going to be 8 factorial, over negative 7 times 8 times 7 times 6 times 5 for the successive taking of the derivative here. And in the end, we get the ratio negative 5 over 7. Of course, we could have predicted that at the beginning, but I wanted to emphasize the L'Hopital's rule here. And when we get that the limit as x approaches infinity is a constant that is not 0, whether the constant is positive or negative, we have an indication that the numerator function and the denominator function grow at the same rate. So this is defining in number 7 the relative rates of growth of two continuous functions as x approaches infinity. We say that two functions have the same relative rate of growth if the limit of one over the other as x approaches infinity is a non-zero constant. If this limit was 5 over 3, then the limit of the reciprocal g over f would be the reciprocal of the limit 3 over 5. F grows faster than g if the limit as x approaches infinity of f over g is equal to infinity. Similarly, that says g grows slower than f. And f grows slower than g if the limit of f over g is equal to 0. In number 8, we're going to consider the ordinary definite integral from 1 to 5 of 1 over x dx. There is no vertical asymptote here and no infinite bound. So we want to sketch rectangles to represent the Rme approximation, and we're going to express the finite sum in sigma notation. Well, we want to identify the x values of 1 and their y coordinates, 2 comma f of 2, 3 comma f of 3, 4 comma f of 4, and 5 comma f of 5. So making the Rme approximation means that we use the left endpoint to create a rectangle for each subinterval. And in this case, we are going to have that the Rme approximation is going to be f of 1 times 1 plus f of 2 times 1. It doesn't say how many rectangles we want to use, and so I'm just going to use rectangles of width 1, which means we're using 4 rectangles, plus f of 3 times 1 plus f of 4 times 1. So the sigma notation in this case is going to be I equals 1 to 5 of, well, we're going to do, actually we can write it differently. We can do I equals 1 to 4, f of I times delta x, which is 1. We can do the Rme approximation, and in this case the Rme approximation will use still 4 rectangles, but we are going to have an underestimate here, and Rm is going to equal, it's going to be, well, let me write it in expanded form first and sigma notation second. It's going to be 1 times f of 2 plus f of 3 plus f of 4 plus f of 5. So there are always more than one way to set up the bounds. We can have I equals 2 to 5 of f of I times 1, or we could set up the sum from I equals 1 to 4 of f of I plus 1 times 1. In this case, the larger is Lrem. Lrem is greater than Rm because f of x is decreasing. And we have that Lrem is an overestimate for the integral, and Rm is an underestimate. This is just getting you thinking in terms of what we did with making rectangles so that we can see series in a sort of accumulation perspective. So now we are going to connect the discrete to the continuous. Let's consider the integral from 1 to 5 of 1 over x root x dx. It's a slightly different function. It's getting closer to the horizontal asymptote at a different rate from 1 over x. We're also going to consider a series with the same p-value. And so the p-value in both cases is 3/2. If we consider 1 over x to the p or 1 over n to the p. X is a value contained in the real numbers, and n for series is contained in the integers, and in this particular case we're saying that n is going from 1 to 5. Write the expression in the integral and the series as a function of t. So we're going to say that f of t is equal to 1 over t to the exponent 3/2, which is the same as 1 over t square root t. And so what's true about the measure of the following? For the interval from t equals 1 to 5, we know that f of t is always positive, and we know that f of t is always decreasing, therefore f prime of t is negative. And so we're going to represent the integral from 1 to 5 graphically. 1, 2, 3, 4, 5 to here. And because we have positive width and positive height, we can think of the integral graphically as not just the accumulation, but specifically with positive width and positive height, we can think of this as the area bounded between the curve and the x-axis, because we have y top minus y bottom, and the y bottom happens to be y equal to 0 for the x-axis. We can determine the value by a quick integration. We have the integral from 1 to 5 of x to the negative 3/2 dx is equal to x to the negative 1/2 divided by negative 1/2, or multiplied by negative 2, from 1 to 5. I'm going to change the bounds and absorb the negative sign. And so we get 2 square root of x evaluated from 5 to 1. Be careful, we see that we have a negative in the exponent, so let's rewrite this properly as 2 over the square root of x evaluated from 5 to 1, which gives us the answer as 2 over root 1 minus 2 over root 5. And the square root of 5 is bigger than the 1 denominator, so the second fraction is smaller than the first fraction, or number, and therefore the result is positive, which makes sense with having a positive height and a positive width. In number 14, we want to represent the series n equals 1 to 5 of 1 over n root n graphically in two ways. Well, we're going to say that this is equal to 1 over 1 root 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus 1 over 4 root 4 plus 1 over 5 root 5. And so we are going to consider that we have each of these terms multiplied by 1, and we can start to see a length times width kind of rectangle. When we ask ourselves how many rectangles we have, we can count 1, 2, 3, 4, 5 different rectangles. This is very different from when we set up the LRAM and the RRAM in the warm-up. Let's go back. When we were doing LRAM and RRAM, we set up the rectangles 1, 2, 3, and 4, and so we had the sum from I equals 1 to 4. Don't forget that the number of terms in a series is given by the top bound minus the bottom bound plus 1. So in this particular case, we have 4 rectangles, 1, 2, 3, 4. But now when we are doing the sum from n equals 1 to 5, the top bound minus the bottom bound plus 1 will give us 5 rectangles. So we can represent the rectangle where the height is 1 times the width of 1 looks like this. And so that would be the A1 term. Then the A2 term, and don't forget that this is still the function f of t, so f of 1 is the same as 1 over 1 root 1. F of 2 is the same as 1 over 2 root 2. And so this rectangle with a height of f of 2 times the width of 1 is A2, which is our second term. A1 plus A2 plus A3 plus A4 and 5. And then we have A3, A4, and A5 actually has to go one step beyond up to 6. So this would be like saying an integral from 1 to 6, but we have the sum from 1 to 5. Well, we could take this series, the same 5 rectangles for A1, A2, A3, A4, and A5, and we can back them up so that we could start like this. So all we're doing is visually or graphically translating each of the 5 rectangles back 1 unit. And so now the A5 rectangle goes between t equals 4 and 5 as opposed to between t equals 5 and 6. It's not necessary how we set it up because as we saw with summations, we can set up a sum from I equals 0 to 4 or a sum from I equals 1 to 5. It doesn't change the value of the sum to change the bounds by translation. So graphically we can translate the 5 rectangles back 1 space and get the same series. A1, A2, A3, A4, and A5. Now, we're not showing here that this is exactly the LRAM and the RRAM, but we are showing how we can take the ideas of rectangles with a width of 1 and connect it to a geographical interpretation of the series. So we could represent each of these values as the sum, as the area of a rectangle whose width is a constant value of 1. So in number 15, we can ask the question true or false and to explain. Is the value of the series from n equals 1 to 5 of 1 over f of t, or f of n, of f of n, is it the same as the value of the integral from 1 to 5? Well, we should be very careful because we know that x is a continuous variable, x contained in the reals, whereas n is a discrete variable contained in the integers. And so when we take a look at the areas that could be represented, if we go back a slide, we could represent the area in red from 1 to 5 between the two boundaries as the area under the blue curve. And whether or not we want to represent the first 5 rectangles or the second sequence of 5 rectangles, the amount of area is going to be the same, whether it's in the first representation or the second representation. However, if we look at the second representation, we can actually see that these 5 rectangles in green produce an overestimate, and therefore we should see that the series value and the integral values are not the same from this example. So I'm just going to refer to the shading in green for the series, and in blue for the integral. And we can see with our function decreasing but having positive terms that the series value is going to be greater than the integral value. So we could change that to a greater than and have a true statement. We want to know, does the integral 1 over x root x from 1 to infinity dx converge? And we know if we were to extend this and go on and on and on, we would see that the integral value would go on forever. And since it's got a p-value of 3/2, which is greater than 1, therefore, yes, the integral from 1 to infinity of 1 over x to the 3/2 dx converges. Now, we know that the value of the series is going to be an amount of area larger than the convergent area for the integral. So by the direct comparison test, we might not actually be able to come up with a comparison to say that, yes, we're going to have a finite amount of green area as the green rectangles go on and on and on forever. So this is kind of still inconclusive. This is inconclusive because it's a bigger amount of area than the integral area, as we have an infinite interval. But we still see that there's some kind of relationship between the amounts of areas in blue and the amounts of areas in green. What we will find is that if the amount of blue area for the function f of x converges, then the amount of green area for f of n will also converge, however, to a different number. What that number is, we might not be able to find. And this result is going to be known as the integral test. So we're going to fill in the box to make a true statement. We can see that the area for the discrete case is going to be greater than the area for the continuous case. So now, with this exploration complete, we are going to talk about why we care about the convergence of series, and then come up with the integral test to relate the sequences, the finite, discrete, rather not the finite, but the discrete case for series with the continuous case for integrals. So as with many definite integrals, it is difficult to find the exact value of s. We can do so for convergent series if r is between -1 and 1. We can also find some telescoped series and come up with an expression for the nth partial sum and then take its limit. But in general, for most series, we cannot come up with the sum. And then we focus on, well, do we even know if the sum exists? Which means, does the series converge? So we are going to be focusing a lot on approximating the value of the series to some accepted level of accuracy. And that approximation is known as an estimate. So the first thing we need to focus on is whether or not the series converges. So what follows is a library of basic convergence tests for series. In this section, we're going to focus on tests for series whose terms are all positive. So we're going to look at the series from from n equals 1 to infinity of a sub n such that a sub n is greater than 0. In 10.4, we will look at what happens if some of those terms are negative. And we are ready now to take the review warm-up material, especially about limits and about integrals, and we are going to come up with 4 tests about convergence of series where the terms are all positive. This would be a good time to pause the video if you want to come back and look at the second half, because it will be a long video. Now we'll continue with part 2, the actual Calc 2 part of section 10.3. The first test we will look at is called the integral test. The integral test says that if an is a sequence of positive terms such that an is the same as the function f of n, where n of course is an integer, and if f of x is a continuous, positive, and decreasing function, much like those graphs that we were just focusing on, for x greater than or equal to n. What that just means is that maybe the function isn't always decreasing, maybe it's increasing and then it starts to decrease at some point. Then we could extract the amount of area or accumulation prior to x equal to n, and then we can apply the integral test and all the convergence part once the series, or the function rather, begins to decrease. So then we can say that either the series made up of the f of n terms and the integral made up of the f of x values either both converge or diverge. So this is very helpful because in 8.9 we started to study how to tell if integrals that are improper converge or diverge by letting t approach infinity and setting up the integral from n to t of f of x dx. This is similar to finding the partial sum Sn, but we do have to be very clear that the integral is not the same as the series. So with this connection between the discrete series and the continuous function in place, we can take a look at the first test, the integral test applied to a series in number 18. So I'm going to leave all of these pictures intact, and I'm going to make them really small, and then I'm going to begin the exercise 18. So in exercise 18, we want to know if this series converges. Well, we first of all need to make sure that the function f of n, we're going to let it be the function given by the an term, namely e to the n divided by 1 plus e to the 2n. And then we want to check to make sure that the function is continuous, positive, and decreasing for some x value after some maximum point. And so we are going to say, first of all, we know that f is continuous because the denominator, because e to the n is continuous, and 1 plus e to the 2n is always greater than 0 for all values of n. The second thing, we know that f is positive, in other words, f of n is greater than 0. In fact, there is no n value for which this function is not positive, so again for all n, because e to the n is greater than 0, and 1 plus e to the 2n is greater than 0, and the quotient of two positive quantities is positive. So we have condition 1 is satisfied, condition 2 is satisfied, and we can check to see that f is decreasing by looking at its derivative. So when we work out f prime of n, we have e to the n times 1 plus e to the 2n minus, so derivative of the top times the bottom, minus the top times the derivative of the bottom, which is 2 times e to the 2n, all over the denominator squared. And we can expand this, we can factor out e to the n, and we're left with 1 plus e to the 2n minus 2 e to the 2n, all over 1 plus e to the 2n quantities squared. So therefore f prime of x is equal to e to the n times 1 minus e to the 2n divided by 1 plus e to the 2n all squared. And let me just make sure that I got that right. In the numerator, we had e to the 2n minus 2 times the same thing. It's going to be negative one of those things. And we know that e to the n is always positive, and 1 plus e to the 2n all squared is always positive. So if we did a quick sign chart, the only roots are going to come from the numerator being equal to 0. So if we set 1 minus e to the 2n equal to 0, we get 1 is equal to e to the 2n, and therefore 2n is equal to 0, and therefore n is equal to 0. If we set the denominator equal to 0, 1 plus e to the 2n equal to 0 implies that e to the 2n is equal to negative 1, but this is false because powers, like e to the 2n, are always positive. And so the only root we have is at n equal to 0. And we can list all of the factors, e to the n, 1 minus e to the 2n, and 1 plus e to the 2n, which is already positive, but squaring it really confirms always positive. And so we're going to get positive, positive, and then here we're going to get, if n is a negative number, like negative 1, we're going to get 1 minus e to the negative 2, which is 1 minus 1 over e squared, which is a positive value. And then for n equal to 1, for example, we will get a negative. And then we get positive, positive for the last row. And this tells us that the sign of f prime of x, or f prime of n, and I'm going to emphasize that I have n, will be a positive first and then a negative second. But we're really interested in the series beginning at n equal to 1. So certainly when n is equal to 1, we are going to have that f prime of n is negative. And since f prime of n is negative, that implies that f of n is decreasing. So because all three conditions of the theorem or test are met, let's just say all three conditions of the integral test are met, we can use the integral test. We know that the series, and let me write the series term as f of n. We know that the series and the integral either both converge, and a symbol for convergence is a downwards arrow, or they both diverge, and a symbol for diverge is an upward arrow. So now all we need to do is decide whether the improper integral converges or diverges, and the series will have the same conclusion. So now we need to check the integral from 1 to infinity of e to the x over 1 plus e to the 2x dx for convergence or divergence. And we do that by rewriting as a limit as t approaches infinity of the definite integral from 1 to t of e to the x over 1 plus e to the x quantities squared dx. We can let u equal e to the x, and therefore du is equal to e to the x dx, and u evaluated at the inner value of 1 gives me e to the 1, and u as a function of t gives e to the t. So this becomes the limit as t approaches infinity of the definite integral from e to the 1 to e to the 2. This numerator is du, and so we get du over 1 plus u squared, which is a basic integral of tan inverse of u evaluated from e to e to the t. So we have the limit as t approaches infinity of tan inverse of e to the t minus tan inverse of e. Now we probably do not know what the composition graph of tan inverse with e to the looks like, but we do know that e to the t can be a power, and powers must be positive. So I'm going to take a look at the graph of y equals tan inverse of x, which is a bounded function by two horizontal asymptotes. And we know that x is the input, and our input of e to the t is only ever positive. So we're going to focus on this part of the graph, which is relevant because we are going to let t approach infinity. So as t approaches infinity, we know that e to the t, which is like our x, approaches infinity. So we want to interpret what the blue y-coordinate approaches as x approaches infinity, and we know that the output value here is going to be the horizontal asymptote y equals pi by 2. So the first limit is pi by 2, and the second limit is a finite number. So we get pi by 2 minus 10 inverse of e. Since this is a real finite value, the limit exists, and therefore we say the integral converges. Since the integral converges, and I will write converges to pi by 2 minus 10 inverse of e. And therefore, by the integral test, having shown that all three conditions are satisfied by the function f of n, we know that the series from n equals 1 to infinity of e to the n over 1 plus e to the 2n also converges. The difference is we don't know how much the sum converges to, and we're not asked. Later on we will talk about estimation techniques for the value of the sum, or for the value of the series. The next thing we want to talk about is the p-series test, which is a special case of the integral test. When we look at integrals of the form integral from 1 to infinity of 1 over x to the p dx, we can talk about an associated or related series. And we will refer to these integrals as p integrals, and we will refer to the associated series as p-series. And so the p-series test is nothing more than the integral test as long as we have that the function is continuous, the function is positive, and the function is decreasing. If that's the case, which is true for the functions of the form f of x equals 1 over x to the p, then we can use the integral test with these three conditions automatically met by functions of this form, and we can refer to the test as the p-series test. What we know then is because these integrals converge when p is greater than 1, then by the integral test having met these three conditions, that the series of 1 over n to the p will also converge for p greater than 1. Furthermore, the p-series will diverge if p is less than or equal to 1. Keep in mind that we are not interested in the p integrals on the interval from 0 to 1 because we want to connect the integral with the infinite series. And we don't want the series to go from 0 to 1 because that will not be an infinite series. Going from 0 to 1 would make a finite series. And we don't ever look at convergence or divergence of finite series. But keep in mind that these two quantities are not meant to be the same, but there is an association by the rectangle approximation method with the accumulation or definite integral of the improper integral. Okay, so let's take a look at number 19. Number 19 says, consider the harmonic series, and we want to refer to it by name because it is a famous series and it comes up a lot. So the harmonic series is going to be n equals 1 to infinity of 1 over n. So it's a p-series with p equal to 1. And it's equal to 1 plus 1/2 plus 1/3 plus 1/4 plus ... So I'm just going to emphasize p-series with p equal to 1. And therefore, by the p-series test, we know that the harmonic series diverges. So we had seen earlier in 10.2 that the limit of the partial sums of the harmonic series did not converge. In other words, the limit did not exist, and therefore the harmonic series diverged. We can also confirm that with the p-series, which is really just a special case of the integral test, where we have functions of the form 1 over x to the p, or 1 over n to the p. So we know that the harmonic series diverges. This is a much easier proof, but it is not as fundamental as the proof that we saw in 10.2. Number 20 asks to determine if this series converges or diverges, and to justify. Then, if the series converges, do we know to what value it does converge? And if we do not know what value the series converges to, determine an upper bound on the sum and represent the upper bound graphically. Well, we know that we have a function 1 over n to the exponent 3/2, and this is a p-series or a p-integral or a p-function, and p is equal to 3 over 2. We don't need to test the 3 conditions of the integral test because functions of this form 1 over n to the p are all positive, continuous, and decreasing. So it's simply a matter of identifying that it is of the form 1 over n to the p. And therefore, well, we can say because p is greater than 1, we simply need to say, therefore the series from n equals 1 to infinity of 1 over n root n converges by the p-series test. However, while we could come up with the value of the p-integral as 1 over p minus 1, it is not true that this series is equal to 1 over p minus 1. This is not the value of the series, it is the value of the integral. So this is equal to 1 over 3/2 minus 1, which is 1 over 1/2, which is equal to 2. And so this 2 is a bound on the series. So let's just take a look at a graph. Let's draw the graph of y equals 1 over x root x. And if we look at it from 1 to infinity, we know that from 1 to infinity, we are going to have a finite amount of area, and that finite amount of area is 2. And the question is, can we come up with an upper bound limit on that area? Well, we know that the shaded area, and I'm calling it area because I have a positive width as well as a positive height. And I know that that red shaded area is equal to 2. And if I wanted to talk about the terms of the p-series, these would be terms of 1 over 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus dot dot dot. And I know that the first term is going to be a rectangle of width 1. The second term can be represented graphically as a rectangle of width 1. The third term, 1 over 3 root 3, can be represented as a rectangle of width 1, etc. dot dot dot. And so in fact 2 is not an upper bound, but rather 2 is a lower bound. So perhaps that's just a typo, or maybe I want you to really just think instead of go into automatic pilot mode on the question. Right? So here we know that the red shaded area is going to be a minimum value for the value of the series. And in fact, 2 is a lower bound for the series with p equal to 3/2. The next test we're going to talk about is the direct comparison test. And if it makes you feel, or remember the comparison test from section 8.9, you are correct. We're going to talk about a series with an being non-negative. So we have no negative terms, which means that the series has terms that are either positive or 0. If the series Cn is a known convergent series, and all of the an terms are less than or equal to the Cn terms, so the an terms for the series we are studying are not higher than the Cn terms, eventually, then the series an converges. So if I have a series, well, let's look at this from a functions point of view. If I had a series where the terms are given a width of 1 apart, then I could really look at the function. And if this is my known series, and I have an unknown series, but the terms are never higher than those other terms, then just like for properties of integrals in the comparison test for integrals, then I know that the amount of accumulation for the unknown series must be less than the amount of accumulation for the known series. So if an is smaller than the terms of the convergent series, then the series an converges. Meanwhile, if an is higher than a series that is known to diverge, then the an series diverges. And so we want to use this direct comparison test to talk about the alternating harmonic series. Can we determine the convergence behavior of the alternate harmonic series by using the direct comparison test with the harmonic series? Well, the alternating harmonic series is going to be the series where every other term changes sign, or every term changes sign. So we have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus ... And here we have terms with negative terms that are negative, so we cannot apply the direct comparison test. Now we can refer to it simply as the comparison test, but we use the word direct because we're talking specifically about the heights of each individual term of one series compared to the heights of terms of another series. So I'm going to put the direct comparison test, but the direct may be omitted, and we can refer simply to the comparison test. We cannot apply the direct comparison test to the alternating harmonic series because the terms of the comparison test, namely that the series cannot have negative terms, doesn't apply. So because this series has some negative terms. But let's just look at it from a point of view of comparison of the heights. We know that each of the terms of the alternating harmonic series are the same or smaller than the terms of the harmonic series. Furthermore, we know that the harmonic series diverges. The alternating harmonic series has to be smaller in sum than the harmonic series because we're going to subtract every so often. So rather than adding a half, we're going to subtract. So we know that the alternating harmonic series is going to be smaller than the harmonic series. But the harmonic series diverges. If the alternating harmonic series is less than that, the alternating harmonic series may diverge or it may converge. So this direct comparison test does not help us to study the alternating harmonic series. We will study it in section 10.4. Now in number 22, we want to find out if the following series converge or diverge. I'll do the first one with you for comparison. We have the given function, or rather the given series has a general sequence term an equal to 1 over 2n plus 3. And I happen to recognize that this is like a p-series term, and the p-series term is going to be 1 over 2n. And so if I have the series of 1 over 2n, I can certainly take the 1/2 in front as a constant and focus on the 1 over 2. So I'm going to let this be a known I know it's a divergent series. You don't have to know if it's convergent or divergent straight away, but since I know that the p-value is 1, this is going to be a divergent series, or lead to a divergent series. So my series of dn is going to be 1/2 the sum from n equals 1 to infinity of 1 over n, which diverges by the p-series test because p equals 1. Furthermore, I know that 2n is less than 2n plus 3, which implies that 1 over 2n is greater than 1 over 2n plus 3. The 1 over 2n series diverges, but the 1 over 2n plus 3 series is smaller than that because I have a bigger denominator. So this means that as far as the 1 over 2n plus 3 series is concerned, cannot be determined to converge or diverge by the comparison test. Now, it would have been wonderful if we had that 1 over 2n plus 3 was greater than the known divergent series, in which case we could say that the given series diverges. But we can't use the comparison test to tell. We do have another test in the case of a series like this, and that other test is called, so what happens if the integral p-series and direct comparison tests are inconclusive, such as this test for this series was inconclusive. We can't use the comparison test, but we do have another test in place. And that test is going to refer to the relative rates of growth of a known series with an unknown series. And so the limit comparison test is going to say if we have two series, one whose convergence behavior we know, so Bn series is the known one, and one whose convergence behavior we are studying, which is the An series, then if we take a limit as n approaches infinity of the ratio of two terms of each of the two series, then we will either get a non-zero constant, 0, or infinity. And based on this, we know if they have the same relative rate of growth, if one grows faster or slower than the other. And so the results are saying if the two series have the same relative rate of growth, and therefore their limit of the quotient is c, then either both series converge or diverge. It doesn't matter if one series is a little bit bigger than the other or a little bit smaller than the other, but if they have the same right end behavior, if they both have a horizontal asymptote, that is a y equal to a non-zero constant, then they have the same relative rate of behavior, or same relative rate of growth, and they have the same convergence or divergence behavior as series. However, if the limit is 0 in this case, part B, then we know that the numerator series, An, grows slower than Bn, and if Bn converges, then An is somehow smaller in its rate of growth than Bn, so it also converges. We are not talking about the direct heights of each of the terms from one series compared with the other. Furthermore, if the An series grows at a faster rate than Bn, and if Bn diverges and An grows faster than that, then the An series must also diverge. So now let's take that same series from the previous exercise and use the limit comparison test to see if we can't finally come up with a conclusion. So here, number 23, let's take a look at A. We want to explore the limit as n equals 1 to infinity of 1 over 2n plus 3 and the convergence behavior of that. Well, I'm going to say that the function or the series that I'm studying has the name An, and I'm going to compare it with a series of Bn terms where Bn I know something about. Again, if I take the series to be n equals 1 to infinity of 1 over 2 to the n, by p series, I know that this diverges. But recall that the heights of the An terms were smaller than the heights of the Bn series. And so I could not use the direct comparison test because smaller than divergent may be divergent or may be convergent. So what I'm going to do now is use the limit comparison test. And in order to use the limit comparison test, I must make sure that my terms in the sequence of An and Bn are positive, which they are. So An is positive and Bn is positive for all n greater than or equal to 1, which is where my sequence is starting. And therefore, I am allowed to use the limit comparison test. So I work out the limit as n approaches infinity of one sequence term over the other. Now, it doesn't really matter which one I put on top, but I want to put the one I am studying, namely the unknown convergence behavior, An term, in the numerator, just for consistency's sake. And then I can put Bn in the denominator as the one I know about. If we had it reversed, then we would just interpret the final answer for whichever function grows faster, slower, or at the same rate as the other. So the limit as n approaches infinity is going to be of 1 over 2n plus 3 divided by 1 over 2n, which is the limit as n approaches infinity. And we don't want fractions within fractions, so I'm going to get 2n divided by 2n plus 3. Now we can go back into a pre-calculus mode or a calc 1 mode and consider that this is a function with real variables with x contained in the reals. And the right end behavior means we are looking for a horizontal asymptote by comparing the leading terms. And we end up that this limit is equal to 2 over 2, which is 1. Because this is a non-zero constant, we can conclude that an and bn have the same relative rate of growth. And this, of course, goes back to the hierarchy of basic functions. Which function grows fastest, which one grows the middle, which one grows the slowest. And we've also talked about that in terms of a hybrid function of variable to a variable. We've also talked about the factorial function when we were looking at the warm-up in section 10.1 or section 10.2. But anyway, we can use L'Hopital's rule if we need to determine the indeterminate limit, and we can understand what the limit value is saying about how an grows compared to how bn grows. Because the two functions have the same rate of growth, and the known series 1 over 2n diverges, therefore we know by the limit comparison test that our series of 1 over 2n plus 3 also diverges. Now the thing is, it doesn't matter if we had actually taken the known series to be 1 over 2n. We could have chosen a different series of 1 over n, which is the harmonic series and also diverges. And if we had chosen 1 over n here instead, then we would have had the limit as 1/2. Because this is still a non-zero constant, it's not about being equal to 1, it's about not being equal to 0 or infinity. We can still say that an and 1 over n have the same rate of growth, and since the series of 1 over n diverges, we can still conclude by the limit comparison test that the series of 1 over 2n plus 3 also diverges. So there's not only just one series or term that you have to come up with. There may be different values or different expressions, and they may lead to different limit values, but they will still conclude the same reasoning or same result about the relative rate of behavior of the an that you are studying and the bn that you know. So go ahead and finish the other exercises for the direct comparison test and the limit comparison test, and you can check your answers with the handout afterwards. The last thing that we want to talk about is the error in estimating the value of an infinite series. And we are going to take a look at a few exercises specifically with respect to the integral test. But first we will define what an error estimate is, what the remainder is of a series. We know that a sum of an infinite series is S, and it's given by the terms a1 plus a2 plus a3 plus ... Well, we can talk about the first n terms, Sn, as a1 plus a2 plus a3 plus ... plus an, which is the nth partial sum. But there are still terms beyond that that go on to infinity. We are going to let Rn, the remainder after the first n terms, or the remainder after the nth partial sum, be given by an plus 1 plus an plus 2 plus an plus 3 plus ... And then, if we know that S is equal to Sn plus Rn, where Rn, remember, I'm going to put this up here, where Rn is the sum of the infinite terms after an, so it's the next term, an plus 1 plus an plus 2 plus ... then we can rearrange and we can solve for Rn as the difference between the entire sum minus the nth partial sum. We can also think of the nth partial sum as the approximation to S. Sn will be a good approximation to S if Rn is small. And so ultimately, because we cannot come up with the value for S for most convergent series, we will have to spend a lot of time coming up with the approximations Sn. Again, Sn, the approximation to S will be approximated by Sn, and it will be a good approximation, and by it I mean Sn, will be a good approximation to S if Rn is small. So the smaller that Rn is, the better Sn is as an approximation to S. So the first thing we're going to do is calculate S10 and S for this series. So S10 is going to be A1 plus A2 plus A3 plus ... all the way up to A10. So it's going to be 1 over 1 plus 1 over 2 cubed plus 1 over 3 cubed plus ... plus 1 over 10 cubed. So it's 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125 plus etc., 1 over 126, all the way up to 1 over 1,000. And now this is a finite sum, so we can work it out. And we will do that. This is one interpretation of the answer, but we could simplify it as another fraction. And so we're going to use the TI Inspire, we're going to use the template, and we're going to create a sum from n equals 1 to 10 of 1 over n cubed. And that sum is equal to that number, which is messy. In fact, I'm just going to take a screen snapshot of it, because I don't want to write it down. And that's the exact value. However, we could also come up with a decimal approximation. And the decimal approximation, maybe I should do them all together. If I approximate this value, we get something that looks like this. Okay, so I'll add all of those here instead. And we can see that that value is approximately 1.1975319, etc., 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 or it's exactly equal to the fraction in the top line. Okay, so that's using the TI Inspire. Now, if we wanted to come up with S exactly on the TI Inspire, I guess it simply remains that we would need to change the bound at the top to infinity. And we'll see what the TI thinks about that. If we change the bound to infinity, it cannot come up with it. So we realize that we're kind of stuck in coming up with the exact value of the sum, but we can come up with some approximations. And we may be able to come up with better and better approximations if we take more terms, but it may take more time and the computing power may not be enough. So I'm actually going to rearrange this now. I'm going to put this over here. And then down here I'm going to put that. Okay, so we can see that we don't like working out S. It's not simplified. So it's like being unable to come up with a closed form, simpler representation. So while this means something, we cannot come up with a number that looks like digits that we understand. Well, so our point in this section then is to use Sn, in this case S10, as an approximation, but we need to know how good the approximation is. In other words, we want to know how small Rn is. So we are going to express Rn as an infinite sum of terms, as an expanded infinite series. So again, recall that S is equal to A1 plus A2 plus A3 plus ... up to An plus An plus 1. I didn't need to break it apart there. I could have broken it apart at A1 and A2. But I'm just going to continue like this. And if we refer to this as the nth partial sum, then that's Sn, and then the remaining infinite series is Rn. So just as a review, Rn is equal to an plus 1 plus an plus 2 plus dot 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 forever. And so therefore we can see that Rn is equal to the sum from I equals n plus 1 to infinity of a subscript I. So Sn is a finite series, but Rn is an infinite series. That's worth writing down. Sn is a finite series, while R sub n is an infinite series. And now we want to interpret this infinite sum, or I should say Rn is the sum of an infinite series and Sn is the sum of an infinite series. It's a minor difference, but it is important. So Sn is the sum of a finite series, while Rn is the sum of an infinite series. Okay, and now we want to interpret Rn as shaded rectangle areas of height ai and width 1. So if we have a graph, and since we are going to be using the remainder estimation in terms of the integral test requires 3 conditions for a function. F must be continuous, positive, and decreasing. So let's just take a function that's continuous, positive, and decreasing. Let's take n right about here. So if we start at n, and then n plus 1, n plus 2, so going a width of 1 apart every single time, and then continuing on forever, then we have some other terms prior to that which represent Sn, but the sum of all of the terms and all of the rectangles after that, of course, are going to be an plus 1 times 1, plus an plus 2 times 1, plus an plus 3 times 1, plus dot dot dot. So height times width of various rectangles. So if this is n, then this is n plus 1, and the height of the rectangle is going to be an plus 1. So this is like an ordered pair, n plus 1 comma a subscript n plus 1, or n plus 1 comma f of n plus 1. And so we have the height here, and we have a width of 1. Well, if we want to start at x equals n, then we have to go backwards. And then we would have all of these rectangles in red like this. Now I'm going to run out of room, so I'm actually just going to imagine that it continues on. Now, if I wanted to start at x equals n plus 1, then I want to start not here, but I want to start here, and I would have to move my rectangles translated 1 to the right. So we know that we are going to have 2 different kinds of representations, but the sum of all the green rectangles, let me just write it like this, the sum of the green areas and the sum of the red areas are the same sums. So those 2 sums are equal. The only difference is, do I start at x equals n, or do I start at x equals n plus 1? But what I do know is that I have a function f here with some blue area. And that blue area, if I write it starting from n to infinity of f of x dx, is actually going to be more than the blue area if I start at n plus 1, because then my blue area is actually going to be the black area, which is going to lose off that first width 1 blue area. And so if I start the integral of f of x dx from n to infinity, I'm going to get a little bit more area than if I start off the integral from n plus 1 to infinity, of f of x dx. And what I know is that the sum of my green areas or the sum of my red areas is somehow in between those two values. Furthermore, the sum of the red areas and the sum of the green areas, this is nothing more than an plus 1 plus an plus 2 plus an plus 3 plus dot dot dot. So these two red and green areas are nothing more than the remainder after the nth partial sum. And I'm finding that my Rn will be bounded in between these two integral values. So here's another picture just to visualize it. I have the function f of x. I have the an plus 1 rectangle, an plus 2, an plus 3, etc. Or I could translate those rectangles forward one space. So I could either start at n or n plus 1 along the x-axis. Either way, this is like the first picture is like my red area. So that's the sum of the red areas, the red rectangle areas. And this picture is the sum of the green rectangle areas on the previous slide. And furthermore, those two quantities, sum of the red equals the sum of the green, which equals an plus 1 plus an plus 2 plus an plus 3 plus dot dot dot, which equals r subscript n. And if I take my area starting from n to infinity under the curve, I have that blue area is more than Rn. But if I start from n plus 1 in a different color, I have that Rn is bigger than the integral starting from n plus 1. And as a result, I have found a lower bound and an upper bound on the estimate, on the how good is the Sn approximation, on the error Rn. So the remainder estimate for integral test says, let an be a series that converges by the integral test. So recall that Fn must be a continuous, we need to put that in there, and positive and decreasing function eventually. And then we have that the amount of error between the actual sum and the approximation Sn, which is called Rn, the amount of error, is bounded below by a definite integral starting at n plus 1 and bounded above by a definite integral of starting from n. And furthermore, if we add Sn, a positive quantity, to all three terms of the inequality, let me rewrite that, it's a bit messy. Let me call this number m for lower bound or minimum, and capital M for upper bound or maximum. Then if I add m less than or equal to Rn less than or equal to capital M, if I add Sn to all of these things, I see that the estimate plus the lower bound is less than or equal to the estimate to the sum plus the error, which is less than or equal to the estimate to the sum plus m. But Sn plus Rn is nothing more than the exact sum S. And so the estimate plus the lower bound and the estimate plus the upper bound on the error are the bounds of the actual sum. So while we may not be able to come up with the actual sum, we may be able to come up with a lower bound value and an upper bound value for what the sum of an infinite series is actually equal to. And so all of this in red is really set again here in bullet points. Now we're going to take a look at an example using the remainder estimate for the integral test. We want to estimate the error in approximating the sum of 1 over n cubed by S10. So we just came up with S10 in the previous example as the sum from n equals 1 to 10 of 1 over n cubed, and we had that really, really long fraction. It was right here, which was approximately 1.19753. This is not the same number as this because it's also an approximation, because we can take more and more digits, and there's probably still more digits here. However, I don't want to write this down, it's too long, so I'm just going to use 1.19753. 1.19753. And so now we want to talk about the error estimate. The error is how far off the estimate is from the actual value. And this is called R10. So R10 is equal to A11 plus A12 plus A13 plus dot 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 forever and ever and ever. So we want to estimate the error. We want to know between what two values does R10 lie. So by the remainder estimate for the integral theorem, we know that R10 is bounded between two other definite integrals. They both have a upper bound of infinity. And when we're looking at the integral of a function, we see that if the function is decreasing, positive, and continuous, then the integral starting at 10 is going to be bigger than the integral starting at 11. So the lower bound is going to go from the integral from 11 to infinity of f of x dx, and the upper bound on the error estimate is going to go from 10 to infinity of f of x dx. And furthermore, f of x is 1 over x cubed. So we know that the integral from 11 to infinity of 1 over x cubed dx is less than or equal to R10, which is all of this, which is how far off our estimate of 1.19753, more or less, is away from the actual value s. And then we have the upper bound, integral from 10 to infinity of 1 over x cubed dx. Well, this is an improper integral, so we can treat it like a limit. We can also use our formulas for the p integrals, but we would have to do an addition of two other integrals first. So we could say that the integral from 11 to infinity of 1 over x cubed dx is equal to the integral from 1 to infinity of 1 over x cubed dx minus the integral from 1 to 11 of 1 over x cubed dx. In other words, 1 to 11 plus 11 to infinity is the interval from 1 to infinity. And so this has a formula of 1 over p minus 1, which is 1 over 3 minus 1. And this is a definite ordinary integral. And so we can rewrite the integrand as x to the negative 3. When we integrate, we get x to the negative 2 divided by negative 2, evaluated from 1 to 11. So we get 1/2 minus a negative 1/2, so plus 1/2 times 1 over x squared from 1 to 11, which is going to be 1/2 plus a half times 1 over 121 minus 1. And so we're going to get, I'm going to rewrite this by factoring out the 1/2. We're going to get 1 plus 1 over 121 minus 1, which gives 1 over 242. So the lower bound is 1 over 242, and we can repeat the process for the integral from 10 to infinity. I'm going to have you try that on your own. I'm going to pause the video to try to shorten it a little bit, and then we'll come up with the final answer to this question. We've worked at the integral from 10 to infinity of 1 over x cubed dx. We now know that 1 over 242 is less than or equal to the error after using 10 terms to approximate the sum of the series, which is less than or equal to 1 over 200. So at most, what does this mean in words? At most, s is equal to the s10 value that we got plus 1 over 200. So s is somewhere between, s is contained from s10 minus 1 over 242 or s10 plus 1 over 200. Well, let's just talk about that for a minute. Let's repeat that. Which number is bigger, 1 over 242 or 1 over 200? We know that the smaller denominator means that the overall fraction is bigger. So the furthest away that s can be is 1 over 200. So give or take. So if we just rewrite this that S is equal to S10 plus R10, R10 is going to be somewhere between 1 over 242 and 1 over 200. So S is going to be somewhere between 1, approximately we said it was 1.19753, plus a number that's in between these two, so at most plus 1 over 200 away, because that's the larger number. Okay, in number 27, we want to know how many terms are needed to ensure that Sn is accurate to within 0.0005 of S. Well, we know that S is equal to Sn plus Rn. We want to know how many terms, so this means to solve for n. So we're going to solve for n such that S minus Sn, which is Rn, is accurate to within 0.0005. So we want the remainder, or the difference between the actual and the approximate values of the series, to be less than 0.0005. So if we can find the number of terms n that makes the maximum amount of error, or difference between the exact and approximate series values, so this is the exact series value, or exact sum, and this is the approximation to S after n terms. So we want that difference to be no more than 0.0005. So if we can find the n value that makes that equal, then we would have the answer to the question. So what we need to do is evaluate this improper integral. And we do that by setting up a limit, and we say that the limit as t approaches infinity of the ordinary integral from n to t of x to the negative 3 dx has to equal 0.0005. So what we're doing is setting up an equation to solve for one unknown. And the one unknown that we are solving for is n. And I don't want to put an exclamation point in case you think it means factorial. So on the left-hand side, when we work out the improper integral, we've got the limit as t approaches infinity of x to the negative 2 divided by negative 2, evaluated from n to t, must be equal to 0.0005. And then we have, I'm actually just going to, no, I'll leave the negative later. The limit as t approaches infinity, I'm going to swap the bounds. And we're going to have 1 over x squared. So we are going to get 1 over 2n squared minus 1 over 2t squared. And that limit has to equal 0.0005. We know that as t approaches infinity, this second term is going to approach 0. And so we get an equation involving only n of 1 over 2n squared must equal 0.0005. And so solving this equation, we get that 2n squared must equal the reciprocal of 0.0005. Well, in fact, I'm going to multiply both sides by 2 first. If I multiply the left side of the equation by 2, I get 1 over n squared. And the 5 doubles to get 10, which gives me 0.001. And then I can reciprocate both sides. N squared is the reciprocal of 0.001. This is 1/1000th. The reciprocal is 1000. And so n is going to be positive or negative, the square root of 1000. But the negative answer is extraneous because n starts at 1. And the square root of 1000 is a number that we need to work out. We do know that 30 squared is equal to 900. So we should be looking somewhere around 31 or 32. And if we take the square root of 1000, we see that it is not given approximately, unless we approximate it. We get 31.6228, more or less. So n is approximately 31.6, but we cannot have a non-integer value for n, so therefore we must take n equals 32. If we choose n equal to 32, we will guarantee that the value that we get as the approximate sum will be within 0.0005 of the actual exact value of the sum. And remember, this is for the sum from n equals 1 to infinity of 1 over n cubed. And so that infinite sum we can figure out if we use 32 terms to a very good precision or accuracy. Okay, the remaining questions that you have here are textbook examples 7 and 8 in pages 602 and 603. This concludes section 10.3 on the integral and comparison tests, including the remainder estimate for the integral test. Please ensure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.